Classification of signals. Introduction. Signals are fundamental in representing information in various forms. The classification of signals helps in understanding their behavior and characteristics. Different types of signals are used across various fields such as telecommunication and control systems. Continuous versus discrete signals. Continuous signals are defined for very instant of time and can take on any value. Discrete signals are defined only at specific intervals and are often derived from continuous signals. The distinction between two types is crucial for signal processing techniques. Analog versus digital signals. Analog signals represent information in a continuous manner, typically using variance in voltage or current. Digital signals, on the other hand, represent information using discrete values, usually in binary form. The transition from analog to digital has revolutionized many industries, improving efficiency and reducing noise. Periodic and aperiodic signals. Periodic signals repeat at regular intervals, making their analysis predictable. Aperiodic signals do not exhibit repetition, making their analysis more complex. Understanding whether a signal is periodic or aperiodic is essential for signal analysis and filtering. Deterministic versus random signals. Deterministic signals can be precisely described by mathematical functions and are predictable. Random signals exhibit variability and cannot be predicted with certainty. Classification into deterministic and random helps in the design of systems for processing these signals. Energy versus power signals. Energy signals have finite energy and zero average power over time. Power signals have finite power and infinite energy, often representing continuous waveforms. This classification aids in understanding the behavior of signals in systems and communication channels. Real versus complex signals. Real signals consist of real valued functions of time and are commonly encountered in physical systems. Complex signals contain both real and imaginary parts, often used in advanced signal processing techniques. Understanding this classification is important for analysis in the frequency domain. Unidirectional and bidirectional signals. Unidirectional Unidirectional signals travel in one direction, often used in simple communication systems. Bidirectional signals can travel in both directions, enabling two-way communication. The choice between these types affects the design of communication protocols and systems. Classification based on frequency content. Signals can be classified based on their frequency content, such as low pass, high pass, or band pass. The frequency domain representation is essential for understanding signal behavior in filters and systems. This classification aids engineers in selecting appropriate filtering techniques for signal processing. Applications of signal classification. Signal classification plays a critical role in telecommunications, audio processing, and medical imaging. It helps in developing algorithms for noise reduction, data compression, and feature extraction. Understanding the classification of signals enhances our ability to design efficient systems across various applications.